We will now discuss the strain Rosette. The stress in a bar subjected to uniaxial stress can be determined experimentally by attaching a strain gauge which is oriented in the direction of stress. After that, the stress is computed in terms of strain by using Hooke's law. The measured strain is generally small, and therefore instruments that are very sensitive are required for measuring it. Previously, strain gauges were mechanical or optical, but these have now been almost completely replaced by electrical gauges. In the case of electrical gauges, we have a wire or a foil element whose electrical resistance varies with its deformation. The gauge is attached to the test specimen, the strain in the specimen being measured as a function of the change in the electric resistance of the gauge element. A single strain gauge oriented in the direction of uniaxial stress is sufficient for computing the stress. For biaxial stress, we might suppose that two strain gauges would be sufficient. This would be true if the direction of the principal stresses were known, but this is not usually the case. To determine the direction of the principal stresses, in addition to their magnitude, we need three values of strain. So, in the preceding article, we determine the strain transformation expression for axial and shear strains. In order to find out our axial strain and shear strain, we need strain X, strain Y, and the orientation of the strain state theta. Unfortunately, there is no equipment that conveniently gives a direct measurement of shear strain gamma xy, so other methods are used. To overcome this problem, we can determine the state of strain uniquely by measuring three linear strains, i.e., strain A, strain B, and strain C. By substituting these three strains in the first expression, we can work out our strain X, strain Y, and gamma XY. The strains are measured at known thetas. So this is what has been done over here. We determine three linear strains, strain A, strain B, and strain C, acting in three arbitrary directions, theta A, theta B, and theta C. We can obtain three simultaneous equations in terms of strain X, strain Y, and gamma XY. Solving these three simultaneous equations will give us the value of strains. As a matter of practical convenience, the linear strains are obtained by using either of two combinations of three resistance strain gauges. The first one is by setting the three gauges with their axes at 45 degrees with each other, whereas the second combination can have three gauges arranged at 60 degrees with each other. These combination of strain gauge arrangement is known as strain Rosette. The three gauges are electrically insulated from each other and are used to determine the strain at the surface of the structure to which they are attached. We can use Mohr circle of strain for each of these rosettes. So in the case of 45-degree rectangular strain rosette, we can have the first strain gauge arranged along particular axis, say X, then another strain gauge arranged at 45 degree, and the third strain gauge arranged at 90 degree with the first strain gauge. Please note, this is not a Mohr circle. This is just showing the 45-degree strain rosette. We can construct a Mohr circle of strain for the 45-degree rosette. In the case of this Mohr circle, we have got the first strain gauge at theta 0, then 2 times 45, the other one is at 90 degree, and the third strain gauge will be at 180 degree. By substituting theta A equal to 0, theta B is equal to 45, and theta C is equal to 90 degree in the three equations, we get strain X is equal to strain A, strain Y is equal to strain C, and gamma XY by 2 equal to strain A plus strain C by 2 minus strain B. These results can be used to construct Mohr circle as shown in this figure. The three strains are 45 degree apart, and these will be represented by three radii CA, CB, and CD, which are 90 degree apart as shown in this Mohr circle. The center C is midway between 2 points G and E. So one side CE of the triangle ACE is known. The other side AE must be computed if we want to construct the circle. The triangles CBF and CAE are congruent. So AE is equal to CF, and based on the geometry of circle, CF will come out to be equal to OC minus OF. Thus, AE will be equal to epsilon A plus epsilon C by 2 minus epsilon B. Therefore, AE will be equal to epsilon A plus epsilon C by 2 minus epsilon B. And CE will be equal to epsilon A minus epsilon C by 2. This will make the radius equal to CA, which will be CE square plus AE square square root. In a similar manner, we can use 60-degree rosette to find out our epsilon x, epsilon y, and gamma xy by 2. Thus, theta will be equal to 0, 60 degree, and 120 degree. And solving again the main strain transformation equation, we will get epsilon x is equal to epsilon a, epsilon y equal to 1 by 3, small bracket 2 epsilon b plus 2 epsilon c minus epsilon a, small bracket close, and gamma xy by 2 equal to 1 by under root 3, small bracket epsilon c minus epsilon b. From these strains, we can construct the Mohr circle and get the remaining unknowns. Now let us do this example in order to understand the use of these expressions. The state of strain at point A on the bracket shown over here is measured using strain rosette shown in figure B. Due to the loadings, the readings from the gauge gives epsilon A equal to 16 to 10 raised to power minus 6, epsilon B equal to 135 10 raised to power minus 6, and epsilon C equal to 264 into 10 raised to power minus 6. Determine the in-plane principal strains at the point and the directions in which they act. Since the strain gauges are arranged in 60-degree rosette, we can use the expression epsilon x is equal to epsilon a, epsilon y is equal to 1 by 3, small bracket 2 epsilon b plus 2 epsilon c minus epsilon a, and gamma xy by 2 equal to 1 by under root 3 epsilon c minus epsilon b. Plugging the values, and we will get epsilon x is equal to 60 into 10 raised to power minus 6, epsilon y equal to 246 into 10 raised to power minus 6, and gamma xy equal to plus 149 into 10 raised to power minus 6. We can determine the center of the Mohr circle by averaging epsilon x and epsilon y. Therefore, 60 plus 246 by 2 into 10 raised to power minus 6 will give us the centroid of the Mohr circle equal to 153 10 raised to power minus 6. Now, our reference strain state is at A, which is having epsilon x equal to 60, gamma xy equal to 149. Remembering that the ordinate in case of strained Mohr circle represents gamma by 2. Therefore, the coordinate of A will be 60 10 raised to power minus 6 and 74.5 10 raised to power minus 6. We can find out the base of this red triangle by subtracting 60 from 153, having the base and the perpendicular of this red triangle known. We can use Pythagoras theorem to determine the radius of the Mohr circle, and the radius will come out to be 119.1 into 10 raised to power minus 6. Now we are asked to find out the in-plane principal strains at the point. Hence, we can determine epsilon 1 equal to 153 plus the radius, which is 119.2, and epsilon 2 equal to 153 minus the radius. And that has been done over here. So epsilon 1 will come out to be 272 into 10 raised to the power minus 6, and epsilon 2 equal to 33.9 10 raised to the power minus 6. In order to find out the plane on which the principal strains lie, we can determine theta p2 by taking tangent theta. Thus, 2 theta p2 is equal to tangent inverse 74.5 divided by 153 minus 60, and we will get 2 theta p2 equal to 38.7 degree and theta p2 equal to 19.3 degree. Now, corresponding to our reference axes, we will have to rotate. If we go counterclockwise 19.3 degree, we will get that axis on which the principal strain occurs.